Section: Introduction. In this section, we discuss the growing interest in model parallelism as transformer models expand in size. We highlight several techniques designed to tackle the challenges of training large models, such as the Zero Redundancy Optimizer, (ZERO), Tensor Parallelism, (TP), and Pipeline Parallelism, (PP). Each method has its strengths and weaknesses. For example, ZERO reduces memory usage by cutting out redundant parameter storage but struggles with high communication costs when gathering parameters and gradients, especially in low bandwidth situations. TP effectively distributes large model parameters across devices but often encounters low computational efficiency and requires extensive communication between devices. In contrast, PP is appealing due to its low communication costs and high computational efficiency, although it faces challenges like pipeline bubbles and high memory usage. Pipeline bubbles occur when certain stages in the pipeline are idle, leading to inefficient use of resources. We note various strategies to reduce these bubbles, including token-level PP and interleaved 1F1B. A notable advancement is zero-bubble pipeline parallelism, which minimizes bubbles by separating the backward pass into two parts, one for computing activation gradients and another for weight gradients. In many PP setups, we store activations from multiple microbatches to lessen pipeline bubbles, which creates a significant memory bottleneck for scaling large models. Previous research has looked into methods like activation recomputation and memory-efficient scheduling to address this issue, but memory constraints remain a major limitation for PP. We focus on an imbalance issue in PP related to vocabulary layers, which is often overlooked but can severely impact performance in terms of both throughput and memory. Typically, transformer layers are evenly distributed across pipeline stages, but the first stage has an extra input layer and the last stage has an additional output layer. This imbalance can lead to pipeline bubbles in other stages due to their lighter workloads. As vocabulary size increases, this issue becomes more pronounced. For instance, with a model like Gemma 29B and a vocabulary size of 256K, the output layer's computation and memory requirements can be about 5 times greater than those of the transformer layers, underscoring the problem. To tackle this imbalance, we propose a new approach called vocabulary parallelism, which aims to balance computation and memory in PP. By distributing vocabulary layers across all pipeline devices, we introduce methods to group computation and communication barriers, along with a flexible scheduling approach that incurs only a small constant memory overhead. Our extensive experiments show that our method significantly outperforms naive layer redistribution and other existing techniques, achieving up to a 51% improvement in throughput. We also review related work on balancing activation memory, where research has focused on the 1F1B schedule. For example, B-pipe transfers activations between devices to reduce peak memory at the cost of increased communication. V-shape scheduling aims for balanced memory usage in pipeline schedules. These methods complement our work, and combining them could lead to a fully balanced pipeline parallelism in both computation and memory. Regarding balancing vocabulary layers, some training systems attempt to address the imbalance by redistributing transformer layers across stages. Deep Speed, for instance, uses a greedy method to automatically balance workloads at the layer level. However, simply redistributing layers has drawbacks. Even after redistribution, compute imbalance can persist, especially when the number of layers per stage is small. Additionally, different layer types have varying compute-to-memory ratios, making it challenging to balance both effectively. Often, rebalancing focuses on compute, leaving memory imbalances, particularly for input vocabulary layers, unaddressed. The effectiveness of redistribution also depends heavily on model and pipeline settings, making it less adaptable. Some models, like Llama 3, reduce one transformer layer from the first and last stages, but this requires architectural changes, which is beyond the scope of our paper. Another method, the interlaced pipeline, distributes input and output vocabulary layers across devices using a tensor parallel style. However, this approach leads to increased peak activation memory and introduces additional pipeline bubbles, making it impractical for real-world applications. Our ablation study indicates that these synchronization requirements can slow down training significantly, further complicating the use of interlaced pipelines. Section Summary. In this section, we discuss the challenges of model parallelism in training large transformer models, highlighting the limitations of existing techniques like zero, tensor parallelism, and pipeline parallelism, particularly focusing on the imbalance caused by vocabulary-related layers. We propose a novel vocabulary parallelism approach to address this issue, demonstrating significant improvements in throughput while maintaining low memory overhead. Section: Vocabulary Parallelism in Pipeline Parallelism. In this section, we address how to divide the vocabulary layers into several computation passes after distributing them across all pipeline devices, while also optimizing the number of communication barriers. We start with a basic approach. In the input layer, each device can independently carry out forward and backward computations. We will focus on the output layer for the rest of this paper. After partitioning the output layer across multiple devices, we can group it into 3 computation passes, which we label as F1, F2, and B. These passes are separated by 3 all-reduce communications that involve the maximum of the logits, the sum of the logits, and the input gradients. We can overlap these communications with the computations of the transformer layer by placing them in a separate stream. However, each of these all-reduce communications introduces a communication barrier across all pipeline devices, complicating the scheduling process. We aim to reduce the number of these barriers by reordering operations in the output layer. Next, we detail the computations in the output layer. Given the output from the last transformer layer and the embedding weights, we first compute Y. Then, we calculate the softmax for each sequence using the local maximum and sum from each device's vocabulary partition. This adjustment allows us to reduce the number of communication barriers from 3 to 2, which we denote as C1 and C2. The operations in C1 involve tensors of a smaller size, which significantly eases the computational load when overlapping with the transformer layer computations. Section Summary. In this section, we introduce vocabulary parallelism to address the imbalance in pipeline parallelism by partitioning vocabulary layers across devices and optimizing communication barriers during computation. We propose algorithms that reduce the number of communication barriers, thereby minimizing activation memory overhead and allowing for more efficient scheduling of vocabulary passes within existing pipeline structures. Section: Backward Phase Optimization. In this section, we observe that all 3 all-reduce communications can occur after we compute the matrix multiplications for the input gradients. We can calculate the derivative of softmax with respect to Y multiplied by W, and the gradient with respect to W beforehand. We then perform the all-reduce operation on the gradient of X after obtaining the values for M_I and the sum of I. Since the matrix multiplications are already done, calculating the gradient of X during the communication barrier only requires lightweight operations. This allows us to complete both phases in the output layer with just one communication barrier, as shown in our algorithm. We note that the weight gradient step can be delayed without affecting other operations, similar to the zero bubble strategy. We compare our 2 algorithms with a naive implementation, showing that by placing operations in a separate stream within the communication barrier, we can overlap them with the transformer layer computations. Although our algorithm introduces a bit more computational overhead, it is still advantageous to reduce the number of communication barriers, which helps save activation memory. In the next part, we present a systematic method to make minimal adjustments to typical pipeline schedules to incorporate the output layer passes. We apply this method to 2 different schedules, 1F1B and V-half. The 1F1B schedule, while popular, suffers from imbalanced activation memory across devices. In contrast, V-half balances the activation memory by using a V-shaped device placement, cutting the memory requirement in half. By integrating vocabulary parallelism into V-half, we aim for a fully memory-balanced pipeline. Regarding scheduling dependencies, we perform output layer computations with 2-in-1 communication barriers in our algorithms, respectively. For each microbatch, we need to integrate the output layer passes, S and T, into the pipeline schedules while adhering to specific constraints. All S passes must occur after the forward pass of the last transformer layer, and all T passes must follow the completion of all S passes. In algorithm 1, the backward pass of the last transformer layer must happen after all T passes, while in algorithm 2, T passes can be delayed. To effectively integrate the S and T passes into typical pipeline schedules while following these constraints, we utilize a framework that structures pipeline schedules based on building blocks defined by the scheduling pattern of each microbatch. By repeating a building block, we can create a pipeline schedule, with peak activation memory calculated by dividing its lifespan by its interval. The lifespan is the time from a forward pass to its corresponding backward pass, while the interval represents the workload of a single microbatch on each device. This method simplifies dependency management and aids in analyzing memory consumption. By inserting 2 or 1 intervals between the forward and backward passes of the last transformer layer, we create space for scheduling the output layer computations. Within the repeating interval, we can schedule the output layer passes arbitrarily on each pipeline device. We provide an example based on the 1F1B schedule, where we follow a 1 forward 1 backward 1 output pattern. The final 1F1B schedules are produced by uniformly repeating the building blocks, and the building block for V-half is detailed in the appendix. For peak activation memory, inserting at most 2 intervals increases it by a maximum of 2 microbatches, which is a small constant overhead. This is a significant improvement over synchronous pipeline schedules, which increase activation memory requirements by 1.5 times. Additionally, the memory savings from balancing vocabulary parameters outweigh the increase in activation memory. Notably, the increase in activation memory in terms of microbatches corresponds to the number of communication barriers, which motivates our optimization of communication barriers. In our experiments, we aim to verify that our schedules with vocabulary parallelism can accelerate performance, achieve balanced memory usage when combined with memory-balanced schedules like V-half, and that the partitioning of vocabulary layers has a reasonable scaling factor compared to linear scaling. Section Summary. In this section, we present a method to optimize pipeline scheduling by integrating output layer computations while minimizing changes to existing schedules, specifically addressing memory imbalances in the 1F1B schedule and enhancing memory balance with the V-half approach. We demonstrate that our scheduling strategies, which include vocabulary parallelism, can improve computational efficiency and maintain balanced memory usage across devices, ultimately reducing activation memory overhead. Section: Implementation. In this section, we implement the pipeline scheduler and the partitioned vocabulary layers using the open-source Megatron LM project. We find that assuming the backward pass takes twice as long as the forward pass can create unnecessary delays, especially when these times vary greatly. Therefore, we profile the runtime of the passes and adjust the scheduling of the S and T passes accordingly. We manage communication groups in separate streams, which allows the communication barrier to overlap with the transformer layer passes. To achieve this, we map CUDA streams to distinct GPU work queues. However, this setup can impact the performance of communication computation overlap in tensor parallelism, which depends on single work queues. To address this, we assign high-priority streams to all model parallel communication groups. We also implement all reduce and reduce as NCCL all reduce to prevent uneven communication loads across devices. Additionally, we pad the vocabulary size to be a multiple of 2 times the number of devices to enhance memory alignment in the vocabulary layers. We observe about an 8% performance increase when using 24 devices with a padded size of 256,032 compared to the original size of 256,008. In all our experiments, we keep the input and output embedding weights separate, but our method simplifies the process of tying these weights since both layers are placed on the same devices. For our setup, we compare several methods using the 1F1B schedule. The baseline is the basic implementation in Megatron LM, which distributes transformer layers evenly across pipeline stages but leads to imbalanced compute and memory. Redis aims to balance computation by redistributing transformer layers across stages. Vocab 1 focuses on vocabulary parallelism with only forward phase optimization, while Vocab 2 builds on Vocab 1 by adding backward phase optimization. Interlaced represents our fully synchronous interlaced pipeline implementation. We test these methods by pre-training GPT-like models of various sizes using up to 32 NVIDIA A100 GPS across 4 nodes connected by a ROS RDMA network. We record the running time of each iteration after several warm-up iterations and compare the 5 methods under fixed model and vocabulary sizes. In our comparison of methods, we present throughput measured in floating point operations utilization and peak memory usage. We find that the layer redistribution approach experiences a significant performance drop of 8% to 33% for large vocabulary sizes, as the output layer has a higher computation cost than other pipeline devices. Its performance also varies based on the model configuration, particularly the compute ratio between the vocabulary and transformer layers. For instance, we see a 9.7% decrease in utilization when increasing the vocabulary size from 64,000 to 128,000 for a 10 billion parameter model with a sequence length of 2048, but this drop is not present with a sequence length of 4096. In contrast, the vocab and interlaced approaches maintain consistent utilization as vocabulary sizes increase. Vocabulary parallelism outperforms the interlaced pipeline in a multi-node setup due to its overlapping communication, achieving 6.7% to 8.2% better utilization for the 21 billion model. For peak memory usage, the naive implementation and layer redistribution methods show imbalanced memory usage, leading to high peak memory for large vocabulary sizes. Although vocabulary parallelism requires some extra activation memory, it becomes negligible as we increase the pipeline parallel size. However, the interlaced pipeline demands 1.5 times more activation memory than the 1F1B setup, causing out-of-memory issues when training the 21 billion model with a sequence length of 4096. We demonstrate that our method can achieve balanced memory usage by applying Vocab 1 on the V-half schedule, which is a memory balanced schedule. This implementation is based on the open-sourced V-half project. To support division into virtual pipeline chunks, we use different configurations in our experiments. We compare the basic V-half schedule with the one that includes Vocab 1. The throughput and peak memory for each pipeline device are analyzed. The basic implementation runs into out-of-memory issues with 32 GPUs and a vocabulary size of 256,000. Similar to previous experiments, the baseline suffers a significant performance drop with increased vocabulary size, while Vocab 1 maintains steady utilization, outperforming the baseline by 7.2% to 143%. Additionally, the baseline shows a considerable memory imbalance across pipeline devices, with differences of up to 45 GB, while Vocab 1 achieves balanced memory usage. Although the first pipeline device holds slightly more parameters due to positional and token type embeddings, the extra memory required is minimal, less than 2.5 GB in our experiments. Section Summary. In this section, we implement a pipeline scheduler and partitioned vocabulary layers using the Megatron LM project, optimizing scheduling to reduce inefficiencies and improve performance by profiling runtime and managing communication streams. Our experiments demonstrate that our vocabulary parallelism methods consistently outperform naive implementations and layer redistribution approaches, achieving balanced memory usage and higher throughput across various model configurations and vocabulary sizes. Section: Scaling Analysis of Vocabulary Layers. In this section, we analyze how well vocabulary layers scale in our vocabulary parallelism implementation. With a vocabulary size of 256,000, we measure the average throughput during all passes across all devices. We compare this to an ideal situation where the throughput increases linearly with the number of devices used. We look at the output layers for vocab 1 and vocab 2 separately. We do not include the time for communications since it overlaps with other computations. The results are presented in a table. We find that parallelizing the vocabulary layers introduces some computational overhead for two main reasons. First, dividing the vocabulary layers reduces the model's utilization of GPU resources because the operations become smaller and less parallelized. Second, there is additional computation required, particularly for the input layer, where all devices must create the output tensor, which does not change in size based on the vocabulary partition. However, it is important to note that both the input and output layers still account for only a small fraction of the total computation in the entire model after partitioning.